Okay. Sure. Okay, the first one, how do I think? I probably told you guys that you need to identify if it's a table question or not. This one is a table question because I have a good living group on a carbon. And for me, this one is similar to alkyl halide. So how do you differentiate if it's a table question or not? We say table question. It's basically the full name. It's substitution and elimination of alkyl halide. So if you see something that says alkyl halide, which means you don't have alcohol or you don't have ROR, which is ether, then we treat this as a table question. So I'll write table here. So that's actually the number one thing that I need to think about. Oh, this is a good living group. In my eyes, that this one is just another alkyl halide. The center carbon is this one, and it has 1, 2, 3 carbon neighbors, so it's tertiary carbon. Good living group, tertiary carbon. This one, can someone tell me what it is?
Strong base.
Okay, it's a small, strong base. So far, you should know what it is. If you don't, go to week 6. Review on the things in week 6. Okay, small, strong base, tertiary. Okay, can we see that? Okay, tertiary, small, strong base. It's going to be E2, okay? So all the orange parts happens in my mind. That's a small, strong base. Then I start to draw the product. It's going to have 2 because it's small. The one that is more substituted. So definitely it's going to be alkane. This one with more substituted is going to be the major. And then it's also going to form something that is not that substituted, which is this one. This alkene has 1, 2, 3. This alkene only has 1, 2. If it's small, strong base, the one with more substituted alkene is going to be the major product. If it's bulky base, which means it's the last column on the table, if it's the bulky base, it's still going to be E2. But this one is going to be the major product. Because your base is bulky, then the base cannot go to the center carbon that easily, or the hydrogen next to the center carbon. Then the things the bulky base is going to do is grab the first hydrogen it can see. Usually it's on the side. That this side, on this side, the hydrogen is like for bulky base, it's easier to grab that one than the one that's kind of have more steric hindrance. Did I make this point clear? Mm-hmm. Okay. So you do need to identify which one is major because they ask major. Okay. The next one is something that you learn in chapter 8, which is the alcohol. So this is something I think this question is good because this is something really handy to use. I will write the product directly. Okay, if you review my reaction map, this is actually one of the way that you can return your alcohol back. Let me find my reaction map. Okay, so last time we talked about alcohol and alkyl halide. How do you turn your alcohol back to alkyl halide? You use this method. It's SN2. So it's SN2. SN2, and it's going to, because previously your alcohol is wet, SN2 give you dash. Good? So this is something that I think is really useful in your synthesis question. If you want to make this alcohol leave, you want to make them into good living group first. So do an SN2, then you can do chemistry on this column. Okay. Next one is another table question. So I'll write table here. So I have a good living group, iodide 1, 2. So this center carbon is secondary. This one is alcohol, which is a weak nucleophile. So on my table, secondary weak nucleophile, is going to be SN1. And then SN1, I hope you all can write the product directly without writing out the mechanism. You should know that this one is going to generate racemic product. Okay? So yeah, question? Did I hear question? No? No question on this one? Yeah, question?
Why is it SN1?
Okay. Because it's secondary, weak nucleophile. Secondary, weak nucleophile.
Oh, okay, yeah.
Questions on this one? Yeah.
Why don't you bond the OH? And why do you have the
Why I don't bond OH?
Yeah.
Okay. So I'm going to still spread out the mechanism a little bit. Okay. This is actually one of the really similar questions in your midterm too. That I see when people draw mechanism. So the mechanism for this one. Okay. The first step is going to be the leaving group leave. SN1 is always like this. So your leaving group leave, you form a secondary carbocation, and this is your nucleophile. So your CH3, CH2, OH is going to attack here. And then I guess this is what your question is. So when it has racemic, it can be wedge or dash. OH, I'll write ET here to save some time. And this one has a positive charge. It still has a pair of lone pair because this oxygen didn't use this lone pair. It only used this pair of lone pair to attack this carbon. So it should have a hydrogen and a positive charge. Then what is that what you are asking, why you don't have that hydrogen? Yeah. It's because you have a positive charge, and we don't want that one. In your product, it's better that you use Lewis space. So Lewis space can be anything. It can be the iodide here or another molecule of alcohol to grab the hydrogen and transfer this bond into oxygen to make it into the lone pair. So finally, your product looks like this. There's this orange lone pair. Okay. Any more question on this one? The next one is epoxide. We talked about that last week. I hope you still remember. If you don't, let's just do this question. First thing, how I think. For epoxide, I hope you still remember that I cut it into half, and if it's going to be basic condition, it's going to attack on the less stereokinase side. If it's an acidic condition, it's going to attack the bulky side, which is the side with more substitute. In this case, this one is a basic condition. How do I know it's a basic condition? It's because I saw leader. This one is a metal. Metal and non-metal are bonded with ionic bond. So for me, this one is minus and plus. This is a strong base. For strong base, just a quick review for strong base. RO minus, which means if this one with another oxygen, not OH, just oxygen, is strong base. R minus is strong base. R minus also includes Grignard reagent, right? H minus is also a small strong base. Actually, H minus is the strongest base among all of them. Okay? So this one is a small strong base. Its basic condition, and it's going to attack on the last steric hindrance side. So the mechanism looks like this. After the first step, so step one, after the first step, the compound looks like this. So I will use the green. I'll use the green one. Okay. After the first step, I didn't touch this side, so I will copy everything down. Oh yeah, bond for me. Okay. And then I didn't touch this this methyl group. I copy everything that's same here. I do have a new nucleophile attaching to it, and it's going to form O-. So pay attention to this. Although I'm drawing it in a way that is not really beautiful, but this one is anti-precision to the bonds with oxygen. So this is anti-precision because it's SN2, and SN2 is always going to be anti-precision. Yeah, question?
Are you able to like turn off a light or something? Because it's really hard to see that way. Like,
Which
it's
one?
like a glare.
Which one?
It's like a glare from like a light or something, but it makes it really hard to see when you're reading.
Turn off
Those
the.
are right there. You can dim them.
Okay.
The white one's over there.
No, over there.
Oh, okay.
There's dim.
I don't know which one is going to work. That's it better?
Yeah, it does help.
Do the rest of the class want to be this or the previous one? So it's fine for you to write? Good? Okay. But it sounds really weird to me. Okay, anyway, as long as you can see. Does it look good on the camera? Can camera see it?
Yes.
Okay, good. Okay. Then the pink, I highlight the part that is in anti-precision. So later on, the second step, so when it's water with hydrogen, so it has a name. It's acid workup. Acid workup. Okay, I just told you guys in quiz that if you have synthesis problem, you cannot combine your two steps into one. This is the only exception. Only if your second step is acid workup, then you can put two steps together. Because we want to avoid a negative charge on our product. The acid workup is we want to use the hydrogen in our acid to make this oxygen minus into hydroxyl group. Only if your second step is acid workup, then you can combine them together. So the second step, which is going to lead you to the final answer, looks like this. And you still have your anti-precision like this.
Question?
Yeah,
So whenever you break an epoxide with stereochemistry, the stereochemistry doesn't change?
you don't.
Okay.
Only to the oxygen.
Only to the oxygen, okay.
Yeah, it's like this one because you're SN2. It's basically only you need to have an anti-precision attack. Then only to the oxygen you need to maintain the anti-stereochemistry. The rest, you don't do any chemistry on those. So what was the previous one? You copy everything back to your answer.
What happens if you didn't get the anti-position?
That is wrong.
Okay.
Probably we still give you some points, but I don't know. Okay. Any question on this epoxide one? Yeah, question?
So that would be under basic. What would be an example of like under acidic? Like
Under acidic is going to be SN1, and what SN1 will give you? Racemic product.
So like like for for step one, what kind of compound would you be working with?
First, in this case, this carbon already have 4 bonds, So even if say acidic condition, this one doesn't work. And then answer your second question, what is your acidic? So that was the page that I gave you guys last time. This is the acidic condition. This is the basic condition. Okay.
Gina, to get full points on the epoxide question, our second step could just be to get to that product step that you just showed.
Yeah, so your second step is going to leave your O- to OH.
Okay.
Yeah. Any more question on this one? Yeah, question?
What's that in between the lithium and the, this is SE, yeah, what's in the center, like, what do you figure out?
Which one? This one? Lithium. And then what? This one. Okay, it's this. It's CH3 2 CH. So this is the 2 methyl group, and then CH. So and then it has a pair of lone pair on that. Make sense? Okay. Any more question on this epoxide question? This is the first epoxide question we met. Good? Okay, let's move on. Next one is table question. Okay, I'll write table here. Table question, let's see what is our center carbon. First, I have 2 good leaving group. This one is secondary. This one is also secondary. So they both are secondary. And SH, what is this one? Good nucleophile, good. It's good nucleophile, and on my table, secondary, good nucleophile. Oh, I need to choose the solvent. This one is polar aprotic. Acetone is polar aprotic, so it's going to be here, SN2. If it's SN2, I will just write the product directly. You should be able to do that right now, okay? So if there's no stereochemistry on the center carbon they gave you, you don't need to show. If there is a stereochemistry on the center carbon they gave you, then you show it. Okay. Then next page. Okay, F is a tricky question. Let me see how many of you write down this. How many of you write down this one? Hands up. Good job. It's one of the questions, one of the answers. Okay, so I'm going to talk you through. I want to talk about this one first. This one has other products, but I need to go them stepwise. Okay. This is something that you haven't learned. Maybe you learned, but I assume that you probably forget. So I'll write the mechanism for this one. So remember, whenever you are doing a reaction mechanism, a reaction question, the only reason that you cannot get the correct product is you don't understand the mechanism. So for this question, I just copied down the reagents. And then it's under acidic condition. So the first step is going to protonate your hydroxyl group. Guys, I'm not only practicing on reaction, I'm also practicing on mechanism with you guys, okay? So draw it with me. After the protonation, you make hydroxyl group into a good leaving group. Then this leaving group is going to leave and form a carbocation. When you form the carbocation, it's going to look like this. So my carbocation is here. Pay attention to this carbocation, it's secondary, and you do have a tertiary carbon next to it. Now what it will happen is hydrogen shift in this case, because on the tertiary carbon, the only thing left is a hydrogen. Now if you want to do a shift, it has to be a hydrogen shift, so it's going to be this one. Your hydrogen is jumping to here, and you form a tertiary carbocation. So this one is a secondary carbocation. This one is a tertiary carbocation. This step is called hydrogen shift. Okay? So I'm going to write the product for both. If you, although you do have a hydrogen shift, it doesn't mean that this one is not going to form the product. You still can have your chloro, which is another part of your HCl. So chloro is still going to attack on this secondary carbocation, which is going to give you this one. So your chloro is here, and it's plus minus. This one with your chloro is going to add to that one. So chloro is still plus minus, but actually this is not a chiral center, but it's because it's SN1. I just show this to indicate I know what happens. Now, which one is the major product? In your case, if you answer tertiary, we will give you full mark. But actually, this is the major product. The reason is the ring next to this carbon is a benzene ring. You are going to learn this in 118b. That's the carbocation next to a benzene ring. It's the most stable carbocation in the world. So I only told you guys tertiary carbocation is more stable than secondary than primary. I didn't told you the one next to benzene ring is more stable than tertiary. So whatever you have, the carbocation next to a benzene ring is going to be more stable than the rest of them. This is something you will learn in 118b. So that's why I say if you say this one is the major product, you did a good job because you do know what a hydration will happen and you draw the correct product. Probably this one is not going to be in your final, but just to let you guys see how tricky those questions could be. Yeah.
Can you use the alcohol itself to attack the carbocation?
Alcohol?
Yeah, the reacting product, the reactant.
Oh yeah, the same molecule of itself.
Yeah.
Yes, you do, but I don't recommend you to write that one off.
So Tina, if we put both of them and we were to say like the second one is the major product, that would still be correct. But what if we put the other one as the major product?
So if the correct answer looks like this, I'll write here. So the correct answer looks like this. Oh, cannot see. Okay, so yeah. So you the first thing is you should write both. But actually this one is going to be the major. This is exercise 9-5 in book. Okay, go ahead to check what the answer to write. Actually, I think they probably still put this one as a major because they will think in your way that you haven't learned this one yet. So I encourage you to just do the exercise in the back of the book, okay? And don't forget, your professor, Neil Schoen, is the author of the book. He probably really liked his own question. Okay. Next one. What is LDA? Good, bulky base. Oh, I should use orange color. Okay. Bulky base. And it looks like this. What is bulky base going to do in this question? E2. Oh, this is not. We talked about how to identify if this one is a table question or not. You need to see if there's an alkyl halide or not. In this case, this one is not a alkyl halide because alkyl halide looks Rx. R equals to CnHn, which means this part is R if you think this is an alkyl halide, but it is not because you have the oxygen. So this is not. I'll write WES here. Is that reminds you something? Yeah, William ether synthesis. Okay, try to do that with William ether synthesis. Okay, it's also good time to practice on, it's already 15, okay. Let me finish the mechanism for this one because this one is important. And I will post the answer key. How about this? I will use the last 15 minutes to do the review. And you are going to get your quiz for this week and for last week and this week in my mailbox. You're good with that? Okay, so I'll try to use the last 15 minutes to do question. So the mechanism for this one, bromo, OH, the first step is your base, which is the LDA, is going to grab, I'll use base, grab the hydrogen on that one. So it's going to form bromo, and O minus. And this one is going to attack the carbon, and this one will form intermolecular ether. Okay? The answer key looks like this.
Do you know what are some hints that like you would know when it turns into
A ring?
Yeah.
Okay, so 4-member ring is okay. 5, 6, 7-member ring is better. After that, probably not.
Okay, but like what are some things that you think, oh, this is gonna turn into a ring? For sure. Yeah.
Also, epoxide is a special ring that you should remember. So 4-member ring is okay because the angle strength is a little bit large, but it's still okay. So when you figure out that it's probably going to form, you count the atom, including carbon, and the things that you want to form a ring. Within this range, they're all good. Yeah. So you first. Yeah.
How will we know for sure that it will form a ring though?
You can never for sure. For this question, because it's William ether synthesis, it's intermolecular William ether synthesis. It's kind of a really classical type of question that you should know. Okay, question there.
But like, if you can actually get a 6, you can get a 6-member ring if you attack, if you use that O minus attack another molecule.
No, because intermolecular is better than you attack something else. Because your oxygen, although it looks like this oxygen is far away from this one, but oxygen in reality is really close, that is in the same molecule. So intermolecular is all in one molecule is always preferred than you are going to attack something else.
In one molecule?
Means this oxygen is closer to this carbon than anything else. Okay. I'll move on quickly. Question number 8. I didn't teach you how to do that. If you see similar question in exam, my advice would be you randomly select a site to open, and you don't need to really look into it, because on this side is primary, on this side is primary, on this side is secondary. So on the page of reaction, there's a bunch of tables. If you have primary, secondary, primary, tertiary, what would happen if you only have one equivalence of HX? In this case, it's one equivalence of HX, and it's primary vs secondary. It's actually going to form SN2 on primary. So in exams, I would just advise you guys to randomly open each side. It doesn't matter if you don't have time to review this part. This should be a question for A-class student. You don't have to do it. You just randomly break ones up, okay? This one is no reaction because this is a tertiary carbon, and in my reaction page, the alcohol part is actually going to give you tertiary alcohol, PCCl Jones is going to be no reaction. This one, you don't need to know the temperature is for Levens, which is another 118A instructor. She actually give you a table that's for primary, secondary, tertiary. What temperature is high enough for E1 to be dominated? This one is tertiary, and the alcohol is actually going to have SN1 and E1. You don't need to know that. In Neil Sean's exam, if he wants you to do E1, he will just put his heat. He won't give you a temperature for you guys to identify which one is that temperature high or low. So this one is going to be the major, and also this one. I'll pick up another question, which is this one. Similar enough. This one is tertiary. This one is secondary. Actually, in the table of Levens, although it's 40 degrees, it's not high enough for a secondary to do E1 dominated. It's actually a low temperature.
So we don't have to memorize temperature?
Yeah, you just need to know if we want you to write E1, we are going to write heat. Okay? Levens will ask you, so this one is actually low temperature for secondary. This one is going to be SN1. Okay. And I will going to do N and K together because K is these two conditions, this one and this one. They both are reducing agents. This one is going to reduce RX and carbonyl. This one only reduce carbonyl. So that's the difference for these two questions. So this one is actually going to be OH. This is going to be a hydrogen, but you don't need to show it if you don't want to. This one, only the carbonyl is going to be reduced, and your chloro is still going to be there. But this is only for the first step. After the second step is another intermolecular William ether synthesis. Your LDA is going to grab this hydrogen. So when this hydrogen is away, it's going to be O minus. So your second step is going to form epoxide. This is actually going to be this. This is the answer. This one, I know it's a little bit fast, but you can stop the video at home to rewatch it. It's going to be SN2 first. SN2 as this is going to give you OH, which looks like this. This is after the first step. The second step, this is Jones. Jones is going to oxidize primary alcohol into carboxylic acid. So this is after the second step. The third step is actually going to be an acid-base reaction. I told you guys H minus is the strongest base in the world. So your final product looks like this. Carbonyl dash. Last one, this is LDA, which is a bulky base. Bulky base is going to grab the hydrogen here. So after the first step, this is going to be O minus. The second step is going to be a SN2 on this primary carbon SN2. Then it's going to give you this. I'm sorry that I don't have enough time to be close on it, but let's just move on to the mechanism part. Because I do want you to at least do one mechanism, okay? Although we did several, the first step of this one, when you see acid, is always going to be the protonation of hydroxyl group. So I will do it quickly. OH, long pair, I. So it's going to give you this. Make hydroxyl group into good leaving group, and leaving group is going to leave. After the leaving group leave, it's going to form a secondary carbocation, but you do have a quaternary carbon next to it, which means in this case, it's not going to be hydrogen shift, it's going to be methyl shift. So this one is actually going to be jumped into here. So this is R shift, alkyl shift, okay? So after the alkyl shift, your structure look like this. No, the carbon cation moves to here. So you don't have this one. And then finally, your iodide is going to attack here. Iodide forms here. And that one is going to be plus and minus. Actually, this one is methyl for this group, okay? Oh, no, not methyl. Not methyl because you have this one. So it's going to be racemic. This one, including the hydrate shift we talked about before, I think it's something that's a little bit difficult, but you do can get it after enough practice. Okay? Good. I still have 5 minutes. How about we take a photo together?
Yeah.
Okay, everyone move into the middle, and I'm going to set the camera.